Hello, welcome back to Electrochemical Engineering. Today I'm going to talk about fuel cell stacks and system design. Here on the left are the bipolar plates. This is from Jülich Research Center in Germany. The display they have showing the sort of serpentine flow field patterns in these bipolar plates. And the bipolar plates are integrated into fuel cell stacks with all the other components. Here is a Bosch fuel cell stack, presumably the stack that's used in the Nikola fuel cell truck. So before we talk about those components though, let's talk about fuel processing and reformation. The idea here is that if you want to use a fuel cell that burns carbon fuel, that uses carbon fuel, you can actually use the heat from the fuel cell to drive a reformation process of fossil fuels. This of course emits CO2 and we're likely to see a lot less of this type of designs or prototypes in the future as we go to CO2 net zero. But look at this first reaction. You have CH4 coming in, that's natural gas, methane, plus water. We can reform that to CO and 3H2O. That's a reformation reaction. Then the second reaction is called water gas shift, and it makes additional H2 and CO2. And then the CO can be selectively oxidized with O2. So this set of reactions generates H2 from CH4. And in fact, this is how much hydrogen is generated industrially today. But you could imagine doing this on board in order to store hydrogen as CH4, which is easier to store. So the system efficiency is going to be overall the net electrical output divided by the energy available from the fuel. We'll talk about how to calculate energies. Here we're going to have the free energy of the input fuels times the mass flow rate divided by the molar mass of those species, minus the free energy of the output products divided by the molar mass of the output products. And the net electrical output here in the numerator is just the total current flowing through the cell times the stack voltage. The stack voltage is going to be the sum of all the individual cells in the stack. We'll get there. Minus the power you need to run the ancillary systems and electrical losses in the cell. You can see on the right here a schematic of a fuel cell system showing the fuel coming in, the oxidant coming in, some sort of processor that might be driving a reforming reaction. You have the cell stack, which we'll break down in a moment, exhausting the products, and the electrical power coming out that needs to be conditioned and converted to the format needed in the various applications you might use the fuel cell in. Now, on the previous slide, we used free energy to calculate the efficiency of the system, but often we take the enthalpy as the total possible energy output. And we do this because this is typical for thermal engines, internal combustion engines, is to use the enthalpy of combustion as the denominator in the efficiency calculus. So the efficiency thus is the net electrical output divided by the enthalpy of combustion. That again is the total current times the total cell voltage minus any losses or ancillary power usage in the fuel cell stack. The enthalpy of combustion is just again the mass flow rate divided by the molar mass of the fuel minus the CO2 and H2O products, where X and Y are the stoichiometric coefficients in the balanced chemical equation describing the combustion of the fuel. So you should be able to take any fuel that has carbon, hydrogen, and oxygen, for example, and combust it with O2, react it with O2 to form CO2 and H2O, and you write a balanced chemical equation for that, and the stoichiometric coefficients go in here. This third equation here now has the number of cells in the stack, NC times V cell, instead of the total stack voltage. Now there are two ways to calculate actually the enthalpy of combustion. One is called the higher heating value. That's where you assume the product is liquid, because when gas condenses to liquid, it releases heat. So you'll get more heat out if your product is liquid. The lower heating value is where you assume the product is gas. And that's because you don't get the enthalpy of vaporization back from your product, so you get less heat out of your system. The system thermal efficiency is just the efficiency of utilization of the fuel, we call it the fuel efficiency, times the thermal voltage efficiency, times the power conditioning efficiency, so how efficient are those power conditioning electronics, and the mechanical efficiency. The fuel efficiency is just the fuel that contributes to current in a fuel cell divided by the total amount of fuel that's supplied. So some of the fuel may not be reacted in the fuel cell and may exit through the stream. And you can see that I can write the amount of fuel that contributes to current in terms of the total current divided by N, number of electrons in the reaction, times F. And you see here N, the number of electrons in the reaction, is just based on the balanced chemical formula. And you can see that for CXHYOZ, if you work it out, the number of electrons involved in that oxidation transfer is just the stoichiometric coefficient in front of the O2 times 4, because we know there are 4 oxidizing equivalents going from O2 to O2 minus. Each oxygen atom changes its redox state by 2. The voltage thermal efficiency is calculated as the voltage efficiency as defined before, which is the ratio of the output voltage to the thermodynamic output voltage, times the ratio of delta G to delta H. Here it is rewritten explicitly with the voltage of the cell divided by the thermodynamic voltage, or the reversible voltage that you would expect based on thermodynamics. So efficiencies for fuel cells are typically given in terms of change in enthalpy, not Gibbs energy like we've discussed before. And this is really historical. As I mentioned, the thermal engine efficiency is typically defined this way. So if you look up the efficiency of an internal combustion engine, it's going to be defined in terms of this thermal efficiency, taking into account the total heat generated by combustion. Now the power conditioning electronics, we can calculate their efficiency. Again, the conditioned electrical power divided by the gross net electrical power from the stack. Or another way to write that is just 1 minus the electrical losses divided by the total power from the stack, or 1 minus the fraction of electricity lost due to power conversion. So you can think about the energy flow as follows. You have your energy from the fuel, intrinsic to the fuel due to the delta G or delta H of the oxidation reaction of the fuel. You have the fuel efficiency, which is governed by the fuel cell and the current you're running at. And of course you lose some fraction of that energy, and this is represented by this loss here. This gives you the thermal voltage efficiency, which you convert to a gross electrical power of the stack. And then that needs to be converted through the power electronics to conditioned power, and this is the net electrical power. Some of that net electrical power is then used to power all the pumps and other components that are needed to manage the entire fuel cell system. So the mechanical efficiency is just 1 minus the fraction of that conditioned electrical power that's used to power all those ancillary pieces of equipment that are needed for the fuel cell to function. So let's talk about a few important metrics for fuel cells. One important metric is the average net power, units in watts. This is the conditioned electrical power output from the fuel cell system minus the ancillary power requirements. Also the nominal, maximum, and minimal voltages. So this is sort of the operating voltage, typical, the maximum operating voltage, and the minimum operating voltage. It's the output voltage of the cell stack, not an individual cell. The cell is made up of typically NC times V cell equals V stack, because you have NC cells in the stack. For system efficiency, as is done in practice, we'll use the lower heating value. This is equation 10.3 in Fuller and Hard. Of course, if you use the higher heating value, your efficiencies look lower. Fuel source. Hydrogen fuel is by far the most common, but there's other types of fuel, for example, industrial natural gas, methanol, and others like ammonia that are of interest. The oxidant source is usually air, but it could be pure oxygen. For example, if you had this coupled to an electrolyzer and you were using it for long duration energy storage, it might be practical and useful to store the oxygen generated on the electrolyzer so you could run your fuel cell in pure oxygen. The weight of the system, the volume of the system. You might also worry about heat and where you're going to send excess heat from the system. For example, typically the atmosphere is the heat sink. And of course, the lifetime, how long the system will last. So when you're designing a fuel cell stack, you want to think about what current should each cell be operated at. Of course, if you have a low current, you have a high efficiency because you have low losses due to ohmic, kinetic, transport, concentration over potentials, but that increases the cell area needed to generate a certain power. It increases the volume, the mass, and ultimately the cost of the fuel cell. So there's a trade-off. Given a specific current density, you need to think about what size cells to use, what shape. This often comes down to thermal issues and mass transfer issues through your flow fields. How will you flow air and fuel? How do you distribute that to the cells and within each cell? So typically there's manifolds that supply fuel to one side of the bipolar plate. We'll talk about that. And manifolds that distribute air to the other side of the bipolar plate with the proton exchange membrane, usually in between, driving the reaction at the two electrodes. So some of the important variables for a stack designer that we care about are, of course, the power, the thermal voltage efficiency, the nominal voltage of the cell stack, that's the entire stack, the number of cells in the stack that are connected usually in series using the bipolar plates, the voltage generated by an individual cell, the area of an individual cell, and the total area. The total area is just NC times the area of an individual cell. And I, the current density, that corresponds to operating at the nominal voltage of the cell. Of course, that nominal voltage is a function of the current density, and here are the expressions for the thermal efficiency and the power as well. And commonly, three specifications come from system level requirements. One is here, the thermal voltage efficiency, which is going to be related to the overall thermal efficiency divided by the fuel efficiency, the mechanical efficiency, and the power conversion efficiency. The other is the gross power of the stack. This is going to be the required power divided by the efficiency by which you can transfer output power to your application, to your requirement. So there's going to be some mechanical losses and some power conversion losses that you need to take into account. And of course, the stack voltage is just the number of cells times the individual cell voltage. There are several ways of hooking up a fuel cell stack. One is called a monopolar stack. And this is a design that you might see actually more commonly in battery electrodes, not very common in fuel cells, where you have a wire, a connection to each negative electrode in the stack and a connection to each positive electrode in the stack. And so every single one of these cells is wired in parallel. But this isn't very efficient because all this wiring makes it complex to assemble. Usually folks use what's called a bipolar stack. This uses a lot less wiring. The current flows through the stack, so the total current is actually lower, even though the current density is the same. So you have less resistance through wires and the ancillary equipment. And a single metal plate, or graphite plate, serves as both the anode and the cathode, so you lower your materials use. So these are the bipolar plates. And what you can see is the anode here and the cathode here with our membrane in the middle. And that membrane is typically going to be Nafion. And this motif is just repeated many, many times. And a single metal layer here serves as both an anode and a cathode, but the membranes in the cells are isolated from each other, so the voltages can add in series. Here's a blow-up of the components of a bipolar fuel cell design. We can define A act as the fraction of the area that's active over the total cross-sectional area of our bipolar plate. We'll see this in a second. More specifically, for example, in this diagram, you can see the active area, where the actual flow channels are, is a fraction of the total area. You have an anode material, and if you remember from our earlier lecture on fuel cells, the anode is typically platinum on carbon, and that's going to be driving the hydrogen oxidation reaction. So there's going to be H2 flowing in, fuel flowing in these channels to supply it. It's going to move vertically here. It's going to flow across the channel, but then be pushed vertically and consumed in the anode. There's the electrolyte phase. Again, when a PEM system, this is typically Nafion. As I oxidize those H2 molecules, I'm going to make H+. That H+ is going to move, driven by electric field, by migration across the Nafion electrolyte phase to get to the cathode. And at the cathode, I'm going to have another flow field, and I'm going to bring in O2 in the gas phase. That O2 is going to be traveling here, forced by a pressure gradient, pumped this direction, and it's going to move up into the catalyst layer at the cathode. And this cathode is also typically platinum on carbon, and you're driving oxygen reduction reaction in this case. Notice this flow field here represents a repeating cell, which has identical function to this flow field here. So this is the bipolar plate right here, and you can see that the plate has flow fields for oxygen in one direction and hydrogen in an orthogonal direction. So I can serve these flow fields, here providing H2, here providing O2, with manifolds that are going to be on the orthogonal sides of my fuel cell stack. And we'll see that in a moment here. The bipolar plates have what's called ribs or landing zones to actually contact the gas diffusion layer. The gas diffusion layer, if you remember, is typically a porous support. It could be carbon fiber, or in an electrolyzer, we call the gas diffusion layers the same thing, and they're typically metal fibers. But it might be a carbon paper, like a Toray paper. And then the electrode material is going to be an ink sprayed on here. Typically for a PEM fuel cell, it's Nafion plus that platinum on carbon. And inside the bipolar plate are the channels, which transport the reactants and products. Here's a top-down view of the fuel cell stack. So they are going to be stacked on top of each other like this. And we're looking at the top of our bipolar plate stack here. On one side, there's going to be an inlet air manifold. So these are basically making connections to all those flow fields, those serpentine channels, those channels that handle the flow of air. And it goes in here and out here. And then if you remember, there's going to be a separate input and output for the fuel. And this is going to be hydrogen. And it's on an orthogonal side of the flow field. And you can see that represented here in this diagram. Here's the oxygen input and here's the hydrogen input. It's on the same bipolar plate, but they're on opposite sides and they flow opposite directions. So the manifolds that supply them with gas can be easily engineered. The stack length, the cell width is shown here on a side view of the stack. You see the repeating elements, the end plates, the inlet fuel manifold, the inlet fuel manifold, the outlet fuel manifold. The oxygen or air manifold would be coming out of the screen and be here. Let's talk now about the utilization of oxidant. So for a PEM fuel cell, proton exchange membrane fuel cell, the utilization is given by the rate of oxygen consumption over the rate of oxygen supplied. We can calculate that simply as I over NFA, where N is the number of electrons involved in the Faradaic reaction. Here, 4 for oxygen reduction. A is the area here actually of the entire cell, so it's going to be AC times NC is going to be A of the whole stack, so it's represented by A here. And then we can write the mass flow rate of the air, that's m dot, times the mole fraction of oxygen in the air, that's about 0.2. Air is about 20% oxygen, divided by the molar mass of air. And that's just going to give us the moles of O2 flowing through the system per second. This is going to be essentially a flux of oxygen through the system. And the top is going to be the current we derive from that oxygen. And if we use all the oxygen, the utilization will be 1. So let's think about how utilization might affect the current voltage curve you measure for a fuel cell. Here's an example where you have 50% utilization versus 10% utilization. What you can see is, of course, when you go to lower utilization by increasing the flow rate, this is increasing flow rate, the mass transfer limiting current increases as expected. We're supplying more reactant. And the voltage at any given current actually increases. So the efficiency of burning the fuel increases as you go to lower utilizations of oxygen. So you might think, why is this? Why does the utilization of oxygen have anything to do with the output voltage? Well, you need to remember that part of the efficiency loss in a fuel cell is eta, mass transport, of O2. So the lower the utilization, the less mass transport over potential I have for oxygen. You can even see this in this figure from Fuller and Harb, where he shows that if you have air coming in one side of the cell, that oxygen is going to be used up, and by the time you get to the outlet, you'll have very little oxygen left. So if you thought about what the polarization curve would look like, at the beginning, there's plenty of oxygen, but by the time you get to the end, your mass transfer limiting current becomes very small, and this is problematic. So you don't want to be operating in a regime where you're using up all the oxygen in the air, as this substantially lowers your performance. Now, typically, if you think about a cell potential versus oxygen utilization curve, you want to operate somewhere here where the cell potential here is a relatively weak function of utilization. And this is because it gives you some design wiggle room. You're never going to make everything identical in your fuel cell. Some of the stack components will have higher utilization than others, and you want to be operating in a regime where there's little change in the output voltage if there's some variance in the oxygen utilization due to geometric variabilities of your cell components. I'll also mention that the airflow affects the water balance in the cell, as the airflow can carry away water from the cell. It also affects cooling and the transfer of heat. And the ancillary pumping energy costs go up as you increase the delta P across the cell to increase the flow rate. Now let's talk about utilization of fuel. The fuel utilization is calculated similarly. It's the rate here of hydrogen consumption over the rate of hydrogen being supplied. Well, the hydrogen consumption is just I over NF times the total stack area, where here N is 2 because it's a 2-electron reaction. We divide that by the mass flow rate of the fuel times the mole fraction of hydrogen in the feed, divided by the molar mass of the fuel, in this case hydrogen. The utilization is defined as 1 over what's called the stoichiometry. 100% utilization means stoichiometric amount of fuel added to the stack. 100% utilization means that all the hydrogen is used up. But it can be hard to get 100% single pass utilization because you must also flow N2 and H2 through the system, plus the mass transport over potentials can be significant. But we can also recycle the F. So if you imagine you have some incoming molar flow rate of fuel, it goes through the stack, some fraction of it gets used, and that effluent can be recycled and re-entered into the stack. So the rate of hydrogen consumption in the stack, again, is the number of cells times the current through the stack, divided by 2 times Faraday's constant. The rate of hydrogen supplied to the stack is just the recycled fuel molar flow rate times the new fuel molar flow rate times the mole fraction of hydrogen. in the feed. We can also write a utilization of hydrogen for the system instead of for the stack. And we can also define a recycling coefficient, which is just the molar flow rate in the recycle loop over the molar flow rate in the feed, given here by this ratio. Remember, NC is the number of cells in the stack. Now let's talk about designing the flow fields, which are incorporated into the bipolar plates. Flow to individual cells is typically parallel, and there are manifolds. So manifolds are gas distribution systems, pipes usually, or tubing, and those are used to distribute the flow of the gases. The flow resistance through the cell is typically high relative to the manifold, so the flow is typically uniform through the cell. The question is, how do you find the best channel design? So one thing we need to remember is the so-called Reynolds number. And this is a dimensionless parameter that helps predict fluid flow. Gas is a fluid, type of fluid. At low Reynolds numbers, flows tend to be laminar, sheet-like flow, while at high Reynolds numbers, flows tend to be turbulent. So turbulent flow, the flow lines might go like this. As the flow is continuing in laminar flow, the velocity profiles are nice and smooth. So the Reynolds number is defined as the flow speed times the density of the fluid times some dimension, typically the channel diameter, divided by the dynamic viscosity of the fluid. We're going to define dH here, this equivalent channel diameter, as 4 times the area of the flow over the perimeter, or 2 times length times width over length plus width. The critical Reynolds number for turbulent flow is typically around 2,000, while the Reynolds numbers for these sort of devices are about 100 for fuel cells. So therefore, we typically have laminar flow. Here's a picture of the laminar flow field in a channel. And what you might see here, for example, is an incoming velocity profile. So these vectors here are representing the velocity, let's say in the x direction, for the fluid. And because of friction with the wall, that velocity profile develops as you move along the channel length until we get to a point where we have what we call fully developed flow. And that's where the velocity profile doesn't change anymore as the fluid flows through the channel. This velocity profile is roughly parabolic here, representing flow through the channel. We can calculate the pressure drop needed to drive that flow from the length of the channel times something called the fanning friction. This is related to the Reynolds number. It's how substantial the walls interact with the flowing fluid. The density of the fluid, the velocity squared, divided by this characteristic dimension. And we can estimate the Reynolds number if we know the length of the cell and the dimension of the flow channel. The power then is just the pressure drop times the volumetric flow rate. That's what length times width times the velocity in the direction here. We actually call this the z direction, this direction along the channel. And so this is a general expression for the energy required to move a fluid is just the volumetric flow rate, the volume per time, times the delta P over which the volume is moved. And you can see here plotting pressure versus distance from entrance from some sort of simulation or analytical solution. You can see the pressure drops, develop at the beginning, and then once you're in fully developed flow, the pressure drops linearly through the channel. You can kind of think about a change in pressure as like a change in voltage. It's a driving force for the flow of mass in this case, where voltage is a driving force for the flow of electrons. Now, in the design, providing equal flow to each cell is important. The distribution of reactants goes to multiple channels and to multiple cells. So let's think through what the consequences are for us supplying too much or too little reactant. One thing that can happen is called fuel starvation. This is when there's not enough fuel to a specific region of the cell. And this can happen because the cells are in series. So the current has to be the same through each cell. So even if one cell has too little fuel and it's pushed into the mass transport limited regime for that cell, there is a large potential that's available through the stack to drive the current through the cell anyways. And if there is no fuel available to be oxidized, guess what? You're just going to oxidize any components of the cells that you're able to oxidize. For example, the carbon flow field or the carbon gas diffusion electrode can be oxidized to form CO2 and proton. This can lead to degradation of the cell, so you don't want any component of your cell to ever run out of fuel. This is made complicated by the variability, i.e. tolerances in the channel. These need to be carefully controlled when manufacturing a flow field, so the utilization is well controlled in every single layer of the stack and every single channel in a given layer. You can think about what the impact of having the dimensions of one cell low compared to the others. These are some expressions that we can go through in class where Fuller and Harb explores this. But basically the idea is, so you could imagine you have a nominal design point here, and you get a utilization of 0.6. Now imagine that your cell is just 10%, that particular channel is just 10% too small. Your utilization might go up to as high as 0.9. And this is bad because you'll be in a fuel starvation regime. So you need good tolerance control in your channels to make sure, even with some error in the system build, you have good utilization and you're never starving the cell. Here's some more examples of flow field designs. This is a straight through parallel flow field. This is a serpentine flow field to have a larger chance for the flowing fluid, the oxygen and the hydrogen to interact. Parallel serpentine, spiral, a mesh, interdigitated. There's all sorts of different designs you can imagine. Serpentine are quite common. Now in such a fuel cell, we also need to think about the water balance. And that's because, of course, the conductivity of the proton conducting membrane depends sensitively on the water content. So we have hydrogen and air in and spent air coming out. There's water produced through the oxygen reduction reaction. Remember, O2 plus 4 protons plus 4 electrons goes to 2H2O. So we're producing water, and we're producing water at the cathode. And we're producing at a rate that is I times A over 2F. We can also calculate the water coming in from the air, and it's just the molar flow rate for dry air times the water to air mole ratio. So this is the fraction of water in air, and this is the fraction of air in air. Similarly, we can calculate the water out. It's just going to be the molar flow rate of air minus the oxygen consumed in the reaction. Notice this 4 here tells you that this is the oxygen reduction reaction, so this is the molar rate of oxygen consumption, times again the ratio of water in the output stream relative to dry air. Now, if you want the spent air stream to be saturated with water so that the membrane is conductive, so that might be one of our design rules, you can set that the output water mole fraction should just be the vapor pressure of the water, which is going to depend on the temperature of the cell, divided by the output pressure. So this is basically telling me that the mole fraction of the output air, the spent gas exiting the fuel cell, is equal to the equilibrium vapor pressure of water. So you know that the membrane will stay 100% hydrated. We can also write the utilization of oxygen as the consumed oxygen, the I times the area of the cell over 4F, divided by the total oxygen flow, which is just the flow rate times the molar fraction of oxygen in your input air. Then you can just do a materials balance and say that the water in plus the water produced has to be equal to the water out. And we know the mole fraction of the water out based on this criteria that the output airstream has to be saturated with water so the membrane stays conductive and is fully hydrated. You might want to take a moment and try to understand all the components in here. We can plot this materials balance as a function of temperature and utilization. And you can see that we want to operate on this line here where we have a nice water management. If we go up in temperature at a given utilization, the cell will start to dry. If we go down in temperature at a specific utilization, the cell will start to flood, i.e. water will accumulate inside the cell at the cathode primarily where it's generated, and this will lead to lower performance, and dry out also leads to lower performance. And this all comes from this materials balance equation. Finally, I want to discuss structural and mechanical issues. One thing is the contact resistances that you get between different layers in a fuel cell, between tabs and things like that, or more generally, anytime you have one metal pressed against another metal. At the microscopic scale, nothing is smooth, and so you have some roughness. And when you press two surfaces together, you only have individual points of contact. The conductance of a contact is just 1 over the resistance, and empirically, it can be given as the contact pressure raised to the beta power times kappa. But just conceptually thinking about this, if you have a rough surface and you increase the pressure, the contact resistance is going to go down. A smooth surface, you're going to start with a lower contact resistance, but even a smooth surface has some roughness, and so increasing the contact pressure also causes the contact resistance to go down. And that's because as you increase the pressure, you increase the number of contact points in their effective contact areas. Sealing is another big issue. We don't want any fuel to escape. We don't want leakage between the fuel and oxygen streams. That could be dangerous. You don't want dripping of water on the ground. There's different types of seals that are made. One is called wet seals. You use a controlled porosity to establish a liquid barrier to gas transport. You can use that in low temperature fuel cells that operate below the boiling point of water. Bonding, for example, epoxies, solders, brazes, glass seals. Compression is commonly used where you have a compliant elastomer. An elastomer is typically a rubber or a gasket to account for surface unevenness. There you go, O-rings and gaskets, and you compress them to get those gaskets to fill all those rough surface areas to prevent any leakage. You also typically want a significant axial pressure. Axial pressure is going to be formed by what's called a tie rod. You can see them in the stacks that connect one side of the cell to the other. And these tie rods push or pull, however you want to think about it, the cell together. So you might have a situation where you have your gas diffusion electrodes, gas diffusion layers, GDLs, your membrane electrode assembly, and then your bipolar plates are on the top and bottom here. And you might intentionally fabricate a system that's, say, 450 microns in dimension. So this would typically be in microns. And you might engineer your tie rods and your stacks such that when you assemble the whole thing, that dimension is compressed to 445 microns or smaller. And so you use this controlled compression to keep everything tightly interconnected to lower the electrical contact resistance and get effective compressive sealing of your gaskets. Now, too high axial pressure, though, leads to what's called plastic deformation and mechanical failure, and it accelerates creep. So plastic deformation is where you're bending and deforming materials. So stress can also be induced by temperature changes if the coefficients of thermal expansion are different for different materials within the cell, which of course they are. So the stress due to that coefficient of thermal expansion difference is related to the difference in the coefficient of thermal expansion. So for example, alpha S is going to be the coefficient of thermal expansion, so how much it expands as temperature changes, how much the volume changes with temperature for the support versus for the material of interest. T naught is going to be the temperature where there is no stress in the system, and T is the active temperature. And this term out front has to do with the elastic modulus of the material, so how easily it is deformed divided by 1 minus the Poisson ratio. And this is really a mechanics term that describes how deformation happens in a material in directions perpendicular to the specific direction of loading. These are very important for fuel cells, solid oxide fuel cells, but low temperature devices like PEM fuel cells, this is not as important. So when the stress on a material is sufficiently large, the deformation becomes plastic. That means it's irreversible. It leads to dislocations or other types of defects in the material, and there's a permanent change to the structure. This is called the yield point, and you definitely don't want to exceed the yield point in your mechanical design of a fuel cell. Creep, on the other hand, is a permanent deformation of a material subjected to mechanical stress that's below the yield point. So this may seem kind of contradictory, but the yield point is typically tested over a short period of time, and creep might happen over years. So you might be applying a stress under which the material won't fail in a short time test, but it will slowly change its structure. Unlike fracturing, which is what might happen if you quickly exceeded the yield point, creep is very slow. And you need to design the stack to take creep into account. And that's where we're going to end for today, and I look forward to talking with you about this in class.